In this video then we're going to look at a part of algebra that's perhaps not often looked at and that people see as a sort of separate branch of algebra. I think it's absolutely integral actually, which is looking at how we work with surds. Now, what is a surd exactly? Well, it can be generally described as a surdic quantity as something that starts maybe with a constant, an ordinary number, but added to that, of course this ordinary number might be 0, but anyway, added to that is some kind of square root. And although it's not always a square root, it nearly always is a square root, so we have a square root of another integer, so let's call that b, and this part of the expression might be multiplied by something which we can call k, okay, which again would be an ordinary integer. Now, what do we mean by surdic quantity, and why do we work with these? Well, this part is known as a rational number, so this is rational, and by rational we mean any number that is either a whole number, an integer, or it it's a quotient of two integers. In other words, it's something like an integer divided by an integer, or what we commonly refer to as a fraction. So it was originally thought that any number could be described as a fraction, that all numbers were rational, but in fact even the ancient Greeks pretty rapidly discovered that sadly that's not the case, that most numbers in fact are what's known as irrational, and this is the irrational part of our surdic expression, or surdic quantity as I'll probably call it for the rest of this video. This is the irrational part, and it's formed very often by this square rooting operation. That's supposed to be a b. The square root, for example, of 2 is, well, let's have a look in my calculator here. So if I take 2 and I square root it, I get the square root of 2 is 1.4, here we go, 4142 135, and so it goes on. In fact, it's irrational. We know it's irrational when our decimal answer doesn't have any pattern in it at all and doesn't recur. In other words, goes on forever, has this long number. Famously, pi is irrational. So pi is 3.1428, and so on and so forth. So that's irrational too. So we know we're in the presence of irrational numbers, and irrational numbers are generated very often by square rooting operations. So most of the integers here, that when we square root them, we end up with these recurring decimals. So that's what an irrational number is, and of course because it's so common and we need to use it so often, if we want to keep our answers in exact form, we don't want to decimalize, if you like, this rooted quantity here. We want to keep it in what's called surd form. We want to keep it under the square root sign here, or radical as it's often known now. So that's what a surd is. It's an irrational number or an irrational quantity, and it can be on its own, so you can just have root 2 or root 3 or root 6 or whatever, but very often in its full form we have a rational number added to the irrational, and we have a rational multiplier as well, but a rational plus an irrational gives an overall irrational answer. So this is a surdic quantity. This is the general form for a surdic quantity. Okay, so that's the theory. The next thing to think about are the properties, and in previous videos we have looked in trigonometry, for example, at working in surdic form, working in exact surd form. So we'll have seen some of these properties already. The first property is if you have something like, very simple, root a times, well, root a times b, and that's the square root of all of that, then you can simplify this. We say this is identical to root A, so root A again, times root B. So what we've done in a way is we've split. You can split the radical sign here to create these two simpler forms, the root A and the root B, and just multiply the two together. So you can happily split a long square root like this if it's multiplied together. What if it's one over the other? In other words, it's a division, so we have something like this. A divided by B. Well, again, we can say this is identical to root A divided by root B. So we got the same idea of we're able to split this larger radical sign. Okay, these are very important. I'll just make that a little bit clearer. Principles, because they allow us to simplify surds, and you might already know how to simplify surds. A lot of maths instruction involves teaching people how to simplify surds, and in this video we're not going to concentrate on that. We're going to assume you know already that surds can be simplified using these properties. Now, what we are going to concentrate on in this video is addition, multiplication, subtraction, fractions, squaring, square rooting, those kind of common operations that we do with ordinary numbers, and we want to obviously do the same, be able to do the same with surdic quantities. So let's start with addition. So a quick run through of these operations. Let's go straight in with an example. So let's say we have 2 root 3 plus, let's say, 1. And let's add to that. In fact, I'm going to write it the other way because I'm going to stick to this format. This is how you will usually see surdic quantities. So we usually start with the rational part of the surd. So we have the 1 first plus 2 root 3. So in that order. And we'll stay consistent with that. Now, let's have 2 plus 3 root 3. Okay. And I've written the one over the other because, just like ordinary addition, it's easier to see if we write them and follow down in the columns. So we've got the 1 add the 2, it gives us 3. Let's put a little addition sign here so we know what we're doing. And we've got 2 root 3, add 3 root 3. Well, that's going to be 5 root 3. So in this sense, it's rather like algebra. The root 3 is like a variable, and we're just adding the variables. So we've got 2 of them here, 3 of them here. Now we've got 5. 5 root 3. And we're done. That's how addition works. Subtraction is going to be roughly the same. So let's use the larger number so that we don't get into any negatives here and unnecessarily complicate what we do. So we start with 2 plus 3 root 3. And we'll subtract. This time we're going to use brackets because it should be clear with subtraction that we're subtracting both terms. So that's why I'm using the brackets. So subtracting the 1 and also subtracting this 2 root 3. And so we've got 2 take away 1, which is just 1. And now we've got 3 root 3, take away 2 root 3, which is just root 3. So addition and subtraction, very straightforward operations, working in the same way as we would with a binomial algebraic expression. Let's now have a look at multiplication. So multiplying. Multiplication. Okay. So now, if we're multiplying, we might take these terms here again. So 1 plus 2 root 3. What we're going to be doing is something very similar to when we expand brackets with algebraic expressions. So 1 plus 2 root 3 times, and let's have that 2 plus yeah, 2 plus 3 root 3, that will work quite nicely. 2 plus 3 root 3. So you can think of this root 3 as is much the same really as a variable, like an x or a y or an a or a b. And then if you know how to do that, in other words, if this was 1 plus 2x times 2 plus 3x, as long as you know how to do that, whether you're using grid method or crab clause or however you do it, foiling, then exactly the same method will work here. So foiling, we do the first terms first, so 1 times 2, so if we write it underneath, equals 1 times 2, well that's just 2. Now, what is slightly different with surdic multiplication is rather than going FOIL, I'm going to do the last term next, because these last terms multiplied together, the 2 root 3 times the 3 root 3, these last terms multiplied together will give us not a surdic form anymore, but a rational number once again. So you see how that works. First of all, the 2 times the 3 will give us the 6. So I can write that down. 2 times 3 gives us the 6, but the root 3 times the root 3, well, root 3 times root 3 is root 3 squared. That's going to cancel out this rooting so that we get root 3 times root 3 equals just 3. Okay, so it's 6 times 3 as my middle term here. Okay, I'll just put brackets around that so you can see that clearly. Now we're going to do the outside and the inner. So the outside is 1 times 3 root 3. Well, that's going to give us 3 root 3. And then the inner terms, that's going to be 2 times 2 root 3, so that's going to be 4 root 3. And then there we are, that's fully multiplied out that those two brackets. And you can see we can combine these as well. So 3 root 3 plus 4 root 3 is going to give us 7 root 3, and the rational numbers here, 2 plus 6 times 3 is 18, so 18 plus 2 is going to give us 20 here, plus our 7 root 3, like that. So that's multiplication, and there'll be no particular difficulty if one of these or both of these were negative. So if we had minus here, that would work out the same. But the normal operation when we've got these surdic quantities is very similar to the algebraic multiplying out the brackets. Okay, so now with division, again thinking algebraically, we think of this more in terms of, let's underline this like we had there, we think of this more in terms of fractions. So how do we work with surdic fractions? Is it much the same as with algebra? Well, slight difference here and slightly more complicated. So we'll take this very carefully. Let's think of something, well, let's use the same, why don't we use the same numbers here? So I'll take our smaller quantity here, 2 plus 3 root 3, and divide by 1 plus 2 root 3. Now, what we say with surds is we prefer not to have a surdic quantity in the denominator. And so we use a technique to remove the surdic quantity from the denominator, which is we multiply by what's called the conjugate. So let me write that out. The conjugate surd. So conjugate surd. And in part 2, we'll just define that a little bit more so you're very clear about what we mean by this term's conjugate. Now, the conjugate surd of 1 plus 2 root 3 turns out to be very, very simple. So nothing complicated about finding the conjugate. It turns out to be 1 minus 2 root 3. So to find the conjugate of a square root type surd, then we simply change the sign here. So we've now got 1 minus 2 root 3. And we're using that as our denominator. Of course, we don't want to change this, so we have to have the numerator as being 1 minus 2 root 3. But the point of multiplying by 1 minus 2 root 3 over 1 minus 2 root 3 is that it will in fact remove the surdic quantity from the denominator. So we only have the surdic, we only have the surdic irrational part of the expression, if you like, in the numerator. And the best way to show you how this works, to understand this, is just to multiply it out, and you'll see why this is such a useful technique. Okay, but the conjugate surd is this expression that we've got in both the numerator and the denominator. So that's the conjugate surd. So once we set it up like this, it's simply a case of multiplying both the numerator and the denominator, multiplying right across and seeing what happens. So here we go. So first of all, let's do the numerator first. We've got we're going to FOIL it, so 2 times 1, so it's 2. 2 times negative 2 root 3. Okay, so 2 times negative 2 root 3 is going to give us negative 4 root 3. So let's write that out, negative 4 root 3. And then we've got 3 root 3 times 1. So that's plus 3 root 3. And then finally we're going to get an ordinary rational number here. So we've got 3 root 3 times negative 2 root 3. So it's negative 6 root 3. Sorry, not root 3. So root 3 times root 3 is just 3. So negative 6 times 3. And in fact, what I think I'll do here so that this doesn't get overcomplicated is just erase this. Because negative 6 times 3 is going to give us 18. So let's just write 18. Negative 18. So a little bit involved, but that's our numerator done. And of course what we're going to do is we're going to join together this minus 4 root 3 plus 3 root 3 to get negative root 3 in the top. So this will become simpler in just one moment. Let's do the denominator though. Now the denominator is where the action is really to be found here. We're going to find that all of the surdic parts, the irrational parts of this multiplication are going to disappear, and that's because we've got this difference in the sign here. Now let's see how this works. So we've got 1 times 1, if we're foiling again. So 1 times 1 is just 1. Then we've got 1 times minus 2 root 3. Well, that's going to be negative 2 root 3. But now we've got 2 root 3 times 1. So that's positive 2 root 3. So it's 2 root 3 minus 2 root 3, which is 0. So when you're using these conjugate surds, it has the effect of removing that middle term, which is the surdic, the rational part of the surdic quantity. So all we've got now is the last terms where we've got 2 root 3 times negative 2 root 3. And that's going to be negative 4 root 3 times root 3. Well, root 3 times root 3 is just 3, so 4 times 3. And all of that, let's just make that a little bit clearer actually, is going to simplify to a rational, straightforward integer. Okay, so let's just do the final simplification. So now we've got negative 18 times, 2 minus 18. So 2 minus 18 will give us negative 16. That's our first term. And now we've got this minus 4 root 3 plus 3 root 3. Well, that's going to give us minus root 3. And now in the denominator, we have 1 minus 4 times 3, which is 12. 1 minus 12 is negative 11. And finally, to complete this, if we want to remove these negative signs, if we multiply through by minus 1, minus 1 through the top will give us 16 plus root 3. And we must do the same to the denominator, so minus 1 times minus 11 is going to give us just 11. So our answer, our simplification, or our answer, if we like to think of this as a division, 2 plus 3 root 3 divided by 1 plus 2 root 3 is 16 plus root 3 divided by 11. Okay, so that's the usual operations: addition, multiplication, subtraction, and division. Finally, I want to look at another thing that you might want to do with a surdic quantity, which is you might want to square it, or you might want to square root it. So if you had, for example, something like square root of a equals, let's say, I don't know, let's use some slightly bigger numbers to make it more interesting, 6 root 2 plus 9. How would you do that? How would you find a? Well, a must equal the square of both sides. So we've now got a. So we square this side as well, and we would end up with a very familiar multiplication technique. So we find the product of 6 root 2 plus 9 times 6 root 2 plus 9. Or we could just write the square sign above there. But let's multiply this out now, just as we did before. So we have, let's start with the first. So we've got 6 times 6, this is 36. Root 2 times root 2 is just 2. And the last, 9 times 9, 18. So 81. 9 times 9, 81. So that's the rational part of our surdic quantity. Now we move on to the middle terms, so the irrational part. So we've got 9, and they're going to be the same. So we've got 9 times 6 root 2. Well, 9 times 6 is 54, and we've got that twice, so we've got twice 54, which is going to be 108 root 2. So there we are, just simplify this bit. So we've got 72 plus 81. 72 plus 81 is going to give us 153. Is that right? Yeah. And then the irrational part, 108 root 2. So the numbers have got quite large there, but you can see the principle of multiplication is basically what we're using there. So very, very straightforward, really, and so this is how we square a surdic quantity and get another surdic quantity that's obviously going to be larger than we had before. Now, what if we wanted to work in the opposite way? So this time we're going to have something like a squared equals, let's use the same numbers, 6 root 2 plus 9. Then what we would have to do is take the square root of both sides to get a. So a equals square root of 6 root 2 plus 9. Okay. So that's our challenge. Can we square root 6 root 2 plus 9? Well, it's not so simple, and there is a way of doing this that's a method that you need to learn if you want to be able to do this. Okay, so the very first thing we do is say, well, this must be, if we want to get this back to a surdic quantity, this must end up being some term that we don't know. Let's use x and y this time. Some term x square root of. So this might end up being the rational part, but even if it's rational, we use this square root sign. So square root of 4, for example, is not a surd. So this is our general term anyway. So we let this equal square root of x plus square root of y, and as I say, this might be our irrational part of our surdic quantity. But anyway, that's what we're aiming for. So we let this term equal that. And this is how we solve it. Because what we find then is if we square both sides of this equation, so that's what we want to do next, to remove this square root sign, we'll end up with 6 square root of 2 plus 9 equal the square of this. So root x plus root y squared. Well, what's that going to be? If we multiply this out, we'll end up with first term, root x times root x, x. Last term, root y times root y, y. Now the middle terms, root x times root y, well that's root x, remember this one up here? Root xy, and we've got 2 of them, so it's going to be plus 2 root xy. And I'm just going to bracket this off because I'm going to compare this now to the quantity I had originally, this quantity here. In fact, I don't know quite why I'm writing it like this, because our general term is we want to have the rational first. So I'm just going to swap that round. So instead of 6 root 2 plus 9, I'm going to write it, and you'll see why I'm being fussy about this, 9 plus 6 root 2. The reason I'm being fussy about this is because I want to compare this x and y, which is the rational part of this expression, to this 9. That gives us a little equation. We can call it equation 1. X plus y must equal 9. And there is a proof, quite simple proof, to show why it is that we can compare like this. But because it's fairly intuitive, I'm not including it in this video. But x plus y, you can take my word for it, must equal this 9 here. And so the 2 root xy, well, that must equal the surdic part here, the irrational part, if you like, 6 root 2. Okay. So how does that help us? Well, if, where am I going to write this? Let's write it here. If 2 root xy has to equal 6 root 2, then I can now remove that 2 by dividing both sides by 2. I can say root xy equals 6 divided by 2, 3 root 2, like that, which gives me a second equation for x times y, or just xy. Because if I now multiply both, square both sides of this equation, so I will remove that radical sign there and just get xy. On the other side, I'm going to have 3 root 2 times 3 root 2. Well, I'm going to have 9 times just 2, because root 2 times root 2 is 2. So 9 times 2, which is going to give me 18. So xy must equal 18. So now I've got simultaneous equations. I've got x plus y equals 9 and xy equals 18. This is a very familiar little problem that we're often come across in quadratics, for example, factorizing quadratics, where we've got one part which is giving us the sum of 2 variables. So we've got x plus y, this is the sum. And here we've got the product of those same variables, x and y. So this is the product. So this is a product and sum problem. And we can very easily solve it by considering what 2 numbers will give us both 18, so put that at the top there, and 9 as their sum. 18 is their product, 9 is their sum. So if we start with 1 and 18? Well, that won't give us the sum of 9. What about 2 and 9? No. But when I come to 3 and 6, you can see that 3 times 6 will give us 18, and 3 plus 6 will give us our 9. So we've got our magic numbers, if you like, here, 3 and 6. So what that must mean is that the square root, so let's write our conclusion over here, I think. So let's call this square root. Square rooting, because that's what we're doing. So our solution, our square rooting of 6 root 2 plus 9 square rooted must be these two numbers, 3 and 6, which we know are x and y, the root of x, doesn't matter which one we use, the root of 3 plus the root of y, and y must be 6. So we've done it. We've got a simplified surdic quantity, and we've shown how to square root what looked like a complicated thing, but we've square rooted a surdic quantity to end up with just two very simple surds. Okay, now in the last part of this video we'll just remind ourselves that square roots can be expressed as in index form, so that we get the square root of a equal to is exactly the same as, it's identical to, we should say, a to the power of a half. Well, that might make us think of a to the power of a third, a to the power of a fourth, and what we do then is we change the radical sign, we just put a 3 in front of it. So before that we had a 2, but we just don't write it because we're so used to this being a square root, so square referring to 2. But when we start getting into higher order roots, then we put the number here, so that's a cube root. Now the good news is that we don't need to worry about this when it comes to ordinary surdic problems. We won't come across cube root surds except in higher order mathematics, so more advanced mathematics. So I'm not going to, in this video, it's beyond the scope of this video, we can say, to deal with cube root surds, but important to know that they do exist. And for example, the conjugate, when you're trying to remove the surd from the denominator in a surdic expression, then the denominator in a cube root would be 3 terms, so it'd be quite different to the conjugate that we use when we're just dealing with square roots. But we're just dealing in square roots in pretty much all the time, so it's not something we need to bother with too much. Okay, let's just summarize this important idea of the conjugate actually. So what we've got is something like, so let's write a heading here, surd. We've got something like, and in fact what we'll do is put the conjugate, we'll multiply by the conjugate, so let's put a heading here like that. And this we can say is the rationalized surd. So let's just have a look at how that works. Okay, so first of all, we don't need a conjugate. If we have something like 1 over root 7, then we just multiply by root 7 over root 7. So that would be root 7, so times root 7 over root 7. And we get, well, just root 7 on the top here, and then root 7 times root 7. So it's sort of unrooted to give us just 7 in the denominator. We can express that, and this is why I left a bit of a gap, we can express that without a denominator at all if we want, of course, by just saying, well, that's 1/7 root 7. Now the conjugate idea that we use very often need to use when we're rationalizing surds is when we have something like, well, let's have 1 over again, 1 plus root 7. So when we have the surd with a rational and an irrational component. So what we do then, as we've seen, is we take that but we reverse the sign. So we multiply in this case by 1 minus root 7, and this is the conjugate of 1 plus root 7. And it's very like the difference of squares in conventional algebra, we could say, in that the middle terms now cancel each other out. So we multiply across 1 times 1 minus root 7, we get 1 minus root 7 in the numerator. And in the denominator, because the middle terms cancel each other out, because you'll have root 7 here, that's the inner, times the outer, plus the outer, which is minus root 7. So you have root 7 minus root 7. You're simply going to get in the denominator 1 minus root 7 times minus root 7 is going to give us minus 7. So the answer is going to be 1 minus root 7 over minus 6. 1 minus 7 equals 6. So minus 6. So that's going to be, let's just write it out. 1 minus root 7, negative 6. And you could put the negative in the numerator. You could change that to root 7 minus 1. You could multiply the 6th through so that you don't have a denominator at all, but I think I would leave it like that. That's really a nice way to leave it. And it shows, hopefully, the important part here is that it shows how multiplying by the conjugate gives us our, our rationalized form without a surd, without an irrational in the denominator. Okay, now finally what I want to do is go back to this squaring and square rooting issue, because I think it's very important and a really useful way to practice your skills in working with surds. So let's now go back to this expression that we had here. So 9 plus 6 root 2, and we square rooted it. So immediately what I'll do, in fact, is change this to index form so that I don't have to keep writing this square root sign. So instead I can just bracket it, put to the power of half, and that means exactly the same thing. So that's 9 plus 6 root 2, the square root of 9 plus 6 root 2. Okay, let's then write the answer, which we found was root 3 plus root 6. But what I'm going to do here now is just check that answer by squaring root 3 plus root 6, and we should get back to 9 plus 6 root 2. Let's see if we do. So again, using index form now, which of course we always do when we're squaring, we write root 3 plus root 6 in brackets and then square the whole lot. And working quite rapidly now, I'm not going to write it out as 2 brackets, but imagine it as 2 brackets and just multiply out. So we've got root 3 times root 3, that's the first expression, giving us 3. The last expression is going to be, the last terms rather, multiplied out, are going to be root 6 times root 6, which is going to be 6, so plus 6. Now, the middle terms of our foiling are going to be root 3 times root 6, doubled, because it's going to happen twice, isn't it? It's going to be root 3 times root 6 and root 6 times root 3, if you like. So it's going to be 2 root 3 root 6. Now we can rewrite that line there as 3 plus 6, well that's simply 9. And this line here we can rewrite as 2 root, joining these together now, root 18. We haven't quite got back to here, which is what we're aiming to do. But if we simplify this part here, so we rewrite the 9, we can now extract a square number from here, if you like. So we can see that this is made up of 9 times 2, so that 9 will come out to be 2 root 9 times root 2. So root 9 times root 2 is going to give us our root 18, so it's just rewriting, if you like, this. And our root 9, well, the square root of 9 is 3. So we have 9 plus 2 times 3, 6 root 2. So this must be correct. Now let's do one more just to finish. 22 minus 12 root 2, the square root of that, it turns out is square root of 4 minus square root of 8. So if you use the method in the first part of the video, and I do encourage you to practice this, you should get this result, root 4 minus root 18. So now let's simplify that straight away. So root 4, of course, is not a surd, so we get the square root of 4 is 2. And the square root of 18, well, root 18 we saw from up here has got to be 3 root 2. So that's our simplified result. Now what we've got to do to check it is square it again. So let's rewrite 2 minus 3 root 2 squared, and see if we get back to this result here, 22 minus 12 root 2. So 2 times 2, 4. Minus 3 root 2 times minus 3 root 2 gives us positive 9 times 2, positive 18. Now we've got 2 times negative 3 root 2, or minus 6 root 2. So that's going to be twice that is going to be minus 12 root 2. Nearly there. 4 plus 18 gives us 22 minus 12 root 2. So again, once you practice this a few times, you get quite quick at it. Very easy to check this, and this result must be correct.